Hello and welcome to PCAP's 7th annual Prairie's Got the Goods Week. My name is Caitlin Rose Seiler, and I am the Stewardship Coordinator with Saskatchewan Prairie Conservation Action Plan, or PCAP. Today, Zhang will be speaking about the cooling effects of wetlands in the Prairie Pothole region of North America. I'd like to start by stating we respectfully acknowledge that we are on the traditional territories of many Indigenous nations and communities, past and present. For millennia, they have worked to protect these landscapes and the life these areas sustain. I'd like to thank these original caretakers and acknowledge the ongoing work and presence of Indigenous peoples in Canada today. Before we get going, I'd like to mention that there are 6 other webinars happening this week for Prairie's Got the Goods Week. Topics include wetlands, biodiversity, wild food, pollination, carbon sequestration, and more. And you can register for these webinars on the PCAP website. Just click on upcoming events and then Prairie's Got the Goods Week. All past webinar presentations can be found on the PCAP YouTube channel, and this webinar will be uploaded there in the near future. And a reminder to our listeners out there, if you have any questions during the presentation, feel free to type into the question section of the webinar dashboard. And if you're on the cell phone app, you can send your question by chat to the organizer, and questions will be answered towards the end of the webinar. I'd like to take a moment to note that financial support for today's webinar is provided by our presenting sponsors, Canadian Forage and Grasslands Association and Wildlife Habitat Canada, as well as our supporting sponsor, Saskatchewan Cattlemen's Association. And in-kind support has been provided by Ducks Unlimited Canada, the National Centre for Atmospheric Research, Global Water Futures, and the Global Institute for Water Security. So without further ado, I'm pleased to introduce today's presenter. Zhang is a postdoctoral researcher at the National Center for Atmospheric Research, NCAR, in Boulder, Colorado, USA. He received his PhD in Environment and Sustainability from the University of Saskatchewan in Canada. His research focuses on the impacts of climate change on the water cycle and ecosystems in North America, with special interest in groundwater resources and prairie wetlands. During his PhD, he completed an internship with Ducks Unlimited Canada, where he applied results from climate models to ecological studies and conservation strategies. Zhang's research is contributing to the understanding and management of the importance of wetland environment in the Canadian prairies, with the goal of ensuring a sustainable future for wetland conservation, which requires collective efforts from all stakeholders. So with that, I am happy to pass it over.
Hi everyone. Good afternoon. Let me share my screen. Okay, can you see it clearly? And just my presentation, the title slides. Okay, here we go. Hi, good afternoon, everyone. My name is Zhang. First of all, I want to thank Caitlin and PCAP for inviting me here today. I have spent my last 6 years in the University of Saskatchewan in Saskatoon, and I got this new job in NCAR just January. So after receiving the invitation from PCAP, I'm really excited, and this feels like a homecoming to me that I really appreciate, and I want to talk about this research I have conducted during one project in my PhD study. So I put it here that NCAR and the University of Saskatchewan as my home institute and supported by the Global Water Future project, Ducks Unlimited Canada. So today we will talk about the cooling effects, evidence cooling effects from the Prairie Pothole wetlands. So first of all, thank you very much for, thanks again for attending this. And so I want to say first that even if I'm not only presenting some of the results, but I also want to use as opportunities to for communications and also learn things from the attendees today. So feel free to contact me or put in any questions if you are interested in my presentation or the research. Thank you very much. So to start with a little bit about myself, I graduated in 2016. I moved to Saskatoon and started my PhD studies in the University of Saskatchewan, working on the climate change and hydrologies. So you can see these photos was me in 2018 and 2021 that I was conducting an internship with Ducks Unlimited Canada. So in the photos, I was measuring the length from the vegetation to the edge of the water. So trying to comparing how much of the waters from the wetlands have reduced the surface area from the start of the spring times. And I received my PhD degrees in 2022. It actually just last summer in June. So I really like Saskatoon, and then now I'm starting my new job in the UNCAR as a postdoc fellow in Boulder, Colorado. When I'm not doing research, I like running. This was in the last year in May in the Saskatchewan Marathon. I ran a half marathon, and also I like skiing. So I'm showing one last figure about me in the Canadian Rocky Mountains. So yeah, trying to get familiar with some of the my personal experiences with the Canadian cultural and prairies here. So after that, let's jump into today's presentations about prairie pothole regions. So first, these prairie pothole regions, as we're familiar, it has a large coverage between the US and Canada. It covers the 3 provinces in Canada from the west to east, Alberta, Saskatchewan, Manitoba, and 5 states in the US, Montana, North Dakota, South Dakota, Minnesota, and Iowa. And the prairie potholes wetlands actually has a very long history. They are They are the results of the decaying ice sheet from the about more than 10,000 years ago. So as you can see from this images illustrating that more than 21,000 years, the large part of the North Americas are covered by this Laurentide ice sheet, and the decaying of the ice sheets formed a magnificent landscape in the North American continents. For example, the Great Lakes between the US and Canada borders and the Niagara Fall, that are the results of this decaying ice sheet. But what's happening in the prairies, we also had this, for example, what's happening in the prairies, we also had this glacial retreat that's left over this called the glacial tube on the top of the surface, where these glacial tubes are clay-rich that have a very low permeabilities and poor drainage, so that this forms of these uneven surfaces of thousands of these depressions, and these depressions form these water holding depressions called the potholes, or you can also refer them as sloughs or wetlands or ponds. They have marsh, vein. They have so many names, but in different area, but they have the same common that they can hold the water bodies and are important parts in the ecosystem. In the next slides, I will show you how are these water bodies are actually contributing or shared by the landscape, by the humans and the waterfowls. For example, on the left figure, I'm showing a diagram between in the center of the North America, where you can see this is the contour of the prairie pothole regions, where you can see these blue figures are showing the percentage of the wetland areas within these large areas, and there you can see more than in the US and the Canada, more than 10 or 20% of the area are covered by these wetlands. And here, these wetlands are providing important ecosystem functions. First of all, they can regulate floodings, can purify water qualities from nutrients, and also they can provide wildlife habitats. by saying that they're shared landscape by human and the waterfowls, because if you look at one particular pixels from the above figure, you can see that in the this is showing a satellite images from the above one pixel. We can see this deep darker colors are showing the water bodies, while the other areas or these are human communities that are closely located right across the landscape, and they have a really close surrounding distance. For these figures, these images, you can see these are also very clear that the uneven or irregular shapes of the water bodies, and then right next to it, you can see the rectangle shape of the croplands. So this is trying to demonstrate how closely these two landscape, wetlands, croplands, they are located in the shared by human. And the next figure is particularly in the summer. If you go out to the fields where you will find these birds, ducks or goose. They come from in the summer or springtime. They fly north from the U.S. or Mexico, stay here over the warm seasons. They will have hatches in the grasslands, and then they look for food in the waters, and then have babies, and then fly back to by the end of September and October. So that's what I want to highlight, that this important landscape, wetlands are shared by humans and the wildlife's habitats. But for today's topic, we are talking about, in particular, the cooling impact from the wetland. Before I talk about the cooling impact, I want to highlight a shared memory that in 2021, that was the heat dome events of the extreme hot events in the 2021 summer. For example, I remember that I was in Saskatoon that year. By the Canada Days, we could have the forecast for in Saskatoon, particularly warmer than 38 degrees Celsius. That was a record high temperature breaking a long history, where most of the residents in the Canadian prairies don't have air conditionings. So it caused a lot of these heat events has caused a huge, more than 500 exceeding death from the heat dome from propagating from British Columbia and also Alberta, Washington, and Oregon, also propagating eastwards from the ridges of the Canadian and sharing the Canada and the US, propagating the northeast in the Alberta, Saskatchewan, and Manitoba. These extreme heat events causing death, but also bring damages to droughts to agriculture. For example, here I'm showing that an example of accumulated precipitation by the end of the summer. As you can see, I started in September the 10th, that the large area in the Canadian prairies receive an anomaly less precipitation across the Canadian prairies, only about 30 to 70% of the precipitation compared to normal years. And then according to a survey by Statistic Canada and AAFC, the Agricultural and Agri-Food Canada, in 2021, the summer, with the harvest yield, they're showing that for the 3 Canadian prairies, for particular canola, spring wheat, you can see I highlighted these columns here, that relatively to the 5 years average yield, that the heat events are have reduced the crop yield for the most significantly in Saskatchewan for canola, about half cut off for the yield, and then for spring wheats, more than 1/3 of the yield due to this heat wave and the drought event in the summer of 2021. So after stating that it is a huge impact from the warmer and extreme heat event, our today's topic I want to highlight is the cooling impact that trying to from contributing from the wetlands. So I hope, or maybe by the end of my presentation or seminars, I can convince my idea that these wetlands are having important cooling contributions, and it's have some good benefits to keep them on the landscape. So the cooling effect, I want to explain it. First of all, I want to explain the cooling effect by showing a simple diagram of the wetlands. The physics behind what's really the cooling. It actually feels very intuitive. If you go outside in the warm and hot days in the summer, when you go close to water bodies, you will immediately feel a cooling breeze coming from the water, and also. But what's the physics behind it is that when you look at this illustration on the left, you can see a water bodies of the wetland pond. You can have the waters and vegetations on top of it. And what's really happening is that I'm illustrating on, first of all, I'm illustrating, for example, what's happening, it has from the sun, you will have the radiations coming from the top, inputting energies from the surface to the surface. And these amount of energies or radiations on the surface will be partitioned into two parts. The first part is called the sensible heat. So the sensible heat, you will have the energy is, according to its name, is the heat that you can sense. That's the energies to warm up the temperature. So these energies are used to rising temperatures. And the second part is called the latent heat. So latent means that you can't actually feel them, but these energies are devoted to evaporate waters, so that the net radiation comes from the suns are used in these two parts. And how these two energies or heat, sensible heat and latent heat, are partitioned are according to, depends on how much of the waters are in these wetlands. So for example, you have more waters in the wetland, you will feel a more cooling impact. But if you don't have the waters or experiencing extensive or long drought period, that the waters on the wetlands are going dry, that you don't feel as much of the cooling compared to. And I also want to highlight that these part of the evaporations from the waters can have a long reaching impact into the atmosphere. They can promote the cloud formations that further blocks the radiations. So these blocks the radiations from the sun, reducing the total input from the sun. And then also imagine when you have the sun, when you have a clear sky day, you immediately feeling hot. But when the day is overcast and more clouds and shadiness, you don't feel as hot in the summer. So these are the physics behind the wetland cooling effect. But how do we want to, how are these cooling effects really working with the Prairie Pothole wetlands? So here I'm showing the Prairie Potholes wetlands have a very strong seasonal cycle. For example, as we know that here I'm showing an example from the springtime. These, as we all know, that in the springtime, this snow melts and rainfalls will the water will run off from the surface, and if there is a wetland, they can collect these surface runoff from the snow melting rainfall. And then these, if the water are too much, become the excessive waters, can form this connected wetland network. These are called the fill and spill processes. Here I have an illustration on the left figure where you can see the on the top, when you have not too much water, you can have these three isolated wetlands from up to down. But if you have this, you can see up to when experiencing a very wet period, then you can have this connectivity, or not usually isolated wetland, but then connected to form this network. That's what's happening in the springtime. but what's happening in the summer is a very different story. In the summers, where you can see here, I'm showing 3 photos time slice from for example, in the spring, April the 15th to July, where you have the summer going through May 16th and July the 9th. You can see the water edges of the water, or the areas of the water, are shrinking, and the volume of the water are drying, and the water body are replaced by the vegetations. So you can see that the waters from the wet to the dry have this transitions really going on from the summer, from spring to summer. So in these 2 processes in spring summer, I'm illustrating that the prairie potholes has these strong seasonal cycles where they have very contrasting features from wetting to the drying regime. And the next slide I will show. So here, so far, I'm still showing small wetlands or individual wetlands or a bunch of wetlands in a connected network. But how are these wetlands seasonal cycle captured in a large regional, for example, in the Canadian Prairie, 3 provinces? So here I'm showing is a satellite images from a global inundation satellite. So I'm highlighting 2 features here. First is the maximum extents, and the second is the seasonalities. The maximum extents are showing that the black contours are the location of this Prairie Pothole region, the boundaries from 3 provinces and the US states. The colors of these 2 figures are showing the maximum extent on the left, meaning how large of the areas are flooded or are inundated or flooded in the maximum extents in one particular time of the year. Where you can see here is the in Manitoba, or the low-lying area in Manitoba and the Red River valleys, Lake Winnipeg, you have this very high extent of the maximum extent of the wetland flooding areas compared to the other. When it goes to Alberta, most of the area are not as strong, not as wet compared to the East Prairie Pothole region. On the right-hand side, I'm showing the seasonality. So seasonality meaning how long of the month that these areas will stay flooded. So these are recognized by the length of the months. So from 0 month at the shortest time to 12 months being constantly flooding. So in the Prairie Pothole regions, we can see most of the wetlands, or most of the areas are flooded not consistently in a year, but there have 2 to 3 months, or up to the northern area, we can have up to 4 months or 6 months of constantly flooding, or the flood that has the standing water body on top of the surface. So these are showing the images from the global satellites, characterizing not only these wetlands in a smaller, isolated or small sizes, but in the really large across the 3 provinces and US states, a few of the states. So next, I want to say that after we end up understanding this in the seasonalities and water cycle and the physics, how do we use a model to capture these cooling effect? Can we represent the wetland processes in the models and use this model to explore the wetlands contribution to the regional climate? That's what we did here in a study with Ducks Unlimited Canada in 2021. So we used the representation of the wetlands in a model called a WRF. It stands for the Weather Research and Forecasting Model, WRF. It's a cutting edge and state-of-the-art regional climate models. So in this model, we can have for example, on here I'm showing a diagram of clouds and rains and snows. That's the input from the atmosphere. But what's important is that if we add in a diagram of wetlands from the previous slides, we characterized by its rain and evaporation, snow drifting and spilling over these processes from the wetland contributions. If we bring these two components together, the wetland components and the climate components, can we answer the questions above, representing the wetland and understanding the wetland's role in regional climate? In particular, I want to highlight three processes and happens in wetlands. First is that in the springtime, the wetland can collect water from snow melt and rain. And the second is the water stays in the wetland will evaporate to the atmosphere. And when the water are exceeding the wetland capacity, it can become the outflows to surrounding areas, creating a wetland network. So after building these these models components together, we can conduct the two simulations, or called the model experiments. We do two sets of model experiments. One is called DEF, or default model setting. So that's the simulation you can think of that's without wetland. So if we don't represent these wetlands in the weather model or the climate model, that will be the result on the first case. And the second case is we adding this wetland storage, is trying to, in particular, these three processes on the left. How are these climate model will respond to the wetlands input? So by running these two sets of model experiments, we can see the compare the changes from these two cases, and then they can be solely attributed to the wetlands contribution. First of all, we look at the first and the most direct input is from the evapotranspiration, or called ET. It's a combination of evaporation from the water and transpiration from the plants. So here I'm demonstrating the ET changes from with and without wetlands. Blue means you can have more wetlands with more ETs with wetlands. So for example, we can see this across the spring and summer months from May to August. I want to highlight this region in the northeast corridors of the Prairie Pothole regions, where you can see the strongest impacts are in the June and July months. You can remember the more blue colors, meaning the more ETs from the wetland. So it's more than about 30 to 40 millimeters per month of the strong evaporation coming out from the wetland if we try to include them. But if we don't include them, these ET will be lost. And it has the strongest impact in June and July, but not so much in May and August. So you can think of that in the May, perhaps you have a sufficient water, but the radiation is not so strong to drive this evaporation. But in the August, where you have the water in the wetlands would already go dry, so not enough water from the wetlands, you can have very much radiations from the sun, very sunny days, but not so much water, that the evaporation can't go very high either. So that's the first impression that the input from that we understand with the directly implementing the wetlands, you can have stronger ETs from the wetlands. The second impact is that these ETs increase the wetland can promote the lower clouds. So here, that's the beauty of the coupling of the wetland model with the atmospheric model, is that you can have these vertical cross sections looking at the cloud formation. For example, here I'm showing also in one particular month in 2006 in May, where you can see the black lines are also showing the contour of Prairie Pothole regions. And then these two dashed lines are showing the cross sections of these two latitude of 52 degrees and 95 degrees west. I want to highlight that here is also, remember, the blue, more blue means more clouds, and more red means less cloud. Where you can see, I want to highlight that when you look at this northeast part of the Prairie Pothole, I can put two other figures on the top and on the right. These are the cross section, meaning that if you look at the vertical profile at these two latitude and longitude, where you can see more clouds are more usually associated with the lower atmosphere, corresponding to about 1,000 meters height. And also, these are very significant in these like 92 degrees west longitude, where you can see the clouds are alongside with the these longitude and with the low bottom of the atmosphere, bottom and but not too much impact in the medium or in the top of the upper of the atmosphere. So that's the idea that the wetlands can not only directly input to the evapotranspiration at a surface level, but also can be transported much higher into the atmosphere for more than 1,000 meters into the and promotes the clouds. In that way, it will have less radiation. And after introducing the ET, evapotranspiration, and clouds, but the next step, I will show you the most important significant attribute. That's the temperature aspect. So here I'm showing the temperature with and without wetland changes. The first row is showing no wetlands. So without wetlands, you can have obvious warm temperatures in the summer months. So these are showing in the colors representing the warmer or cooler. So if the more red, meaning the higher the temperature change, and you have if you have so these are also the time evolution for the 4 months from May to August, where you will see the first row without wetlands have the most obvious warmer temperature in the summer months. And then in the middle row is that if we put into wetlands, you will have these wetlands are less red colors along this whole domain, where you have the much alleviated the summer warm temperatures compared to wetlands. And lastly, compared to no wetlands, sorry. The lastly on the bottom row is the direct contrasting between if we put into wetlands and no wetlands. When you look at the large scale temperature change, adding this cooling effect of wetlands area can be as large as 1 to 2 degrees. They are also most strongest in June and July months, not very much in May and August. So that comes to a very strong impacts that the wetlands are having cooling impacts in the whole domain. But then these are we're looking at this monthly average temperature. But what's come back to our extreme temperature experience? How will the wetland contributing to the cooling under the extreme conditions? To do this, we look at one historical event in 2006. I have to note that I did this research in 2021. At that time, that the record-breaking summer heat wave didn't occur in 2021, so I can only study one event in 2006. Well, I want to highlight this period from the middle of July to the beginning of August, where you can see this long extending period of time, about 2 weeks of time. The temperatures on Saskatchewan are breaking the records, setting by this. You can see this mark of the dash line showing a mark for extreme temperature, and then the blue lines are from if we don't have including these wetlands, you always have the warmest temperature along this 4 months period starting in May, you can see it's always breaking the temperature, setting the temperature mark by this black dash line. And then if you have the wetlands impacts, you usually have the lowest temperature along this 4 months period, especially, for example, for many of the days that, for example, in here in the beginning of June, that if you don't have wetland, it will absolutely break in the high extreme temperature mark. But if you have this, you can have this 1 to 2 degrees of cooling. So you can have, I put it in a title, it will reduce the heat wave days and the heat wave intensity by lowering the temperature. And then finally, that's the main takeaway from our study today. I want to have a summary slide here that what the prairie pothole wetlands are doing in the cooling effect. What's doing is that it can store waters from snow and rains. It can promote evapotranspirations and then reduce the latent heat flux by these red arrows, showing a reduced temperature effect. And what's also doing is that it can form clouds that block the solar radiations on the atmosphere. And these impacts are the strongest in June and July than May and August. By the end of so these are the main takeaway from my presentations. So is that let's keep this wetlands if I am making this statement convincing enough. But the next, I want to also highlight the two aspects is that these wetlands are under threats, mainly from two perspectives. One is from the drainage and one is from climate change. We will look at these two aspects one at a time. So from the drainage part, this is what we did in 2021 study with Ducks Unlimited Canada. So Ducks Unlimited Canada put together this drainage map of qualitative 3 stages. First is called the low drainage, and then medium drainage and high drain score. So in the low drainage area, you can see this wetlands have these dark water bodies showing the wetlands across the landscape. And then in the medium drain score, many of the wetlands are already gone. By this, you can see that the waters by the deep colors are gone in this period on the western part of these photos. And then in the high drain area, only the large water body can remain. All those smaller details of the wetlands are drained. So on the left-hand side, on the top is showing the map of these 3 categories of drainage occurring in the 3 Canadian prairies. So most of the areas, 3 provinces, Canadian prairies, we have the blue color or the low drain categories. But if you look at on the northeast edge in the Saskatchewan or Manitoba, that's what's the most drainage happening in the medium and high drain area. And then I also want to share one study with our colleagues from University of Saskatchewan in Domanski in 2015. So in this study, she's showing a time evolution of the drainage, where you can see the ponded area by the blue colors, and then the drainage network channels are showing in the red channels. So giving in the last 5 decades or 6 decades up to now, you can have you should have a lot of the ponded wetland, but to 2009, much of the area already drains in the Smith Creek. It's in the southern Saskatchewan by the area close to Yorkton. So these are from the drainage. I also want to have a question, have the impact from climate change. So this is a study from Johnson and showing the temperature, the favorable climatic conditions for habitat breeding in the prairie pothole. So the red means the favorable area, and in the B, C, and D, we are giving 3 scenarios of temperature warming, and then temperature warming plus more in rain, and then temperature warming combined with less precipitation, less rain. So obviously we're more confident with the temperature warming, and then you can reduce much of the favorable breeding area and the historic. But then if we combine with more waters, more in the rains, you can have some recovery in the southern part. But what's the worst case is that you combine with the warmer temperature and drier precipitation, that you can only have the southern bits in Iowa that's favorable for breeding. And lastly is that is also our colleague working with collaborators from Beeman. He's a professor in the University of Wyoming, showing that the climate change has a huge loss of grassland habitats from climate change. In this figure, we're showing a 3x3 figure matrix by the three time slides of 2030, 2060s, and 2090s in the 3 rows. And the 3 columns are showing the 3 climate scenarios from the low emission to medium and the very high end emission for the carbon dioxide or the greenhouse gases. So we can see that by contrasting the most important, like the lowest or the earliest climate change with the lowest emission, and contrasted with the highest emission by the end of the 2090, where you will have the most of the grassland will be lost to climate change impacts by the end of 2020 in a very high end emission scenario. So the takeaway of this is that the beauty of this analysis is that it can have 3 time slides and 3 scenarios, giving us choices that if we take actions earlier and with the reduce of the global greenhouse gases emissions, we can still have some save much of the habitats. And finally, this is my last slide with the ending remarks here. We can have demonstrating the prairie pothole wetlands have multiple valuable benefits, especially I talked about the cooling effects are important for humans, crops, and birds. And finally, these are especially very critical during the extreme heat wave events. Remember, if you have the 1 to 2 degrees crossing or the 3 under the extreme temperature, you can have reduce not to the record breaking from 38 degrees to 36 degrees, and then you can have much of the coolings if you have these surrounding wetlands near to you. Thank you very much. I have left a one figure of as necessary potholes and my emails here. Feel free to contact me if you have interested in this study and have any questions. Thank you very much. That's the end of my presentation.
First of all, thank you very much. That was really great. And I want to thank you too for your enthusiasm. I know you're really excited about the work that you've been doing. So thank you so much for sharing that with us.
Yeah, thank you.
To our attendees, if you have any questions, feel free to type it into the questions section of the webinar dashboard. Otherwise, you can send it by chat. I just want to mention while we wait for people to send in a couple questions, that this is the first of 7 webinars, so please feel free to check out the PCAP website to register for the other ones. PCAP also has a YouTube channel you can subscribe to and get notified when there's new webinars being uploaded. And we'll also create a playlist for the 2023 Prairie's Got the Goods Week. So a couple questions have come in. Sorry, there we go. So a listener named Ellie is wondering, is there a tool that models the most efficient distribution of cropland versus wetland for a given area to optimize yields and ecological services?
Yes, thank you very much. I want to go back to one slide here. Is actually that is one study I have been working on with this figure. There's one study actually before we're doing the cooling impact is that we had an internship with Ducks Limited Canada. The research question is to ask how will the climate change impacts on the wetland distributions. So that we only look at the climate change impacts on the wetland distribution. But then this question is interesting, asking how to leverage between wetlands and croplands to have this optimized wetland distribution and cropland distributions. So there is some models working on this, but there are some benefits and also some deficiencies. So I want to highlight many of the global model when we talk about climate change or talk about many of the models are from globals. So the global models has very coarse resolution. So 1 pixel are most likely representing 50 kilometers up to 1 degree is about 100 kilometers in the spatial scales. So what my study in with Ducks Unlimited Canada is that we used a 4 kilometers climate downscale data sets to drive a machine learning model called GAM, generalized additive model to use to optimize the GAM model to look at how the impacts of climate change on the wetland distribution. But I'm sure that you can also do statistical models or dynamic models trying to look at the change into the changing from the wetlands to croplands. For example, we also can do this cooling impacts that if we migrate or change the wetlands to cropland expansions, then how will the temperature change? How will the crop yield change? But yeah, of course, that's our interesting study research question.
Absolutely. Cameron is wondering, how does the number and size of wetlands impact temperature scenarios? Do fewer large wetlands equate to a higher number of smaller wetlands? Or is there a geographic network of smaller wetlands more beneficial?
Yes, yes. This is a very great question. So when it comes to the yeah, but so I have to say first that our study are working on a 4 kilometers grid cells. So at these scales, it's not sufficient to understand in particularly like the number of size that how are these numbers like a smaller but multiple wetlands versus large wetlands with less numbers, given they are perhaps they have a similar total area or total volume of water. But I have to say I couldn't answer this question on top of my mind, but it has to be really great focus for many of the study. Yeah, of course. Sorry, I couldn't provide a
No
short answer.
problem. No problem. Jessica's wondering that when you were pulling data to look at averages, what was the date range used? Were you using the last 5 to 10 years or the last 20 years?
Oh, okay. Yeah, thank you. Thank you very much for these questions. I can explain it to you with this figure. So here I'm looking at the extreme temperature in the events in 2006. The dashed lines are looking at the last 30 years of the extreme mark, showing that if the temperature are exceeding this, it's the very extreme in the last 30 years period. So yeah, I'm showing it's the 30 years extreme temperature records. But if you are asking me about this temperature average of the month, I was looking at the 13 years period from 2000 to 2013. These 4 months daily temperature in particular from the last 13 years period. So by the beginning of this century.
Okay, perfect. Thank you for that answer. And Clinton's wondering if you can explain the buffering effects of wetland evaporative cooling and relative humidity impacts on effective rainfall supply for cropland.
Okay, thank you very much. I want to go back to one of the slides that was showing. I'm thinking probably asking about this question. So you said effective precipitation. That is the term for rain, like the rainfall minus
The
evaporation.
effects of wetland
Oh,
evaporative cooling and relative humidity.
yes, yes, definitely. So yes, so um, so here this is the diagram showing the energy balances, or in the academic term called energy balances. But what's really happening is that imagine you have a surface energy budget, we call budget, that you have the radiation coming as the input, like how much of the energy received on the surface. And then if you have these two partitioning term as the outgoing of the energy, if you have more waters, then more um, energy will go into these latent heat flux. So transporting the energy that used to evaporate waters instead of rising temperature. So yeah, that's of a relative contribution compared to. So if you have a more latent heat fluxes, then sensible heat fluxes will be reduced. Then you don't have much energy to rising the temperature, so that but more energy to transmit or evaporate the surface water to rise of the relative humidity. If that's yeah, so the impact is cooling, but also humidifying. That's a rising up of the relative humidity. Yeah.
Okay, so the wetland evaporation will raise the relative humidity
Yes,
and
that's right.
therefore reduce evaporation from cropland. Is that right?
Um, not at this moment. We're looking at the
Okay,
wetland in particular, but not as much for the cropland. No,
okay,
not too much.
okay.
But
That
to
is
do this, we have to look at both sides. So here we only look at the wetlands, but if you're wondering about croplands, that of course we can do this for a future study, like bringing these two landscape together.
okay. Perfect. Thanks for that answer. Um, and another listener is wondering if there are any surface extent data sets along with the global inundation extent from multi-satellites. Um, GIEMS was only available during 1993 to 2007.
Yes,
Do
yes,
you-
thank you. I think let me go back to these slides. Yeah, that's right. When we are doing this study, we used the 25 years records from yes, from 1992 to 2017. Yeah, that's the 25 years records. But I also want to say that there are some other available data set. For example, I think it's called a European Union has a data set called the Surface Water Explorer, Surface Water, Global Surface Water Explorer, GSWE. It's also monthly data of but the resolution is much higher. It's a 30-meter grid cells, so has but also if you have a higher resolution, of course you will increase the amount of data volume and then the size where you have to do a very detailed analysis of the 30 meters. But yeah, but go check out the Global Surface Water Explorer.
Okay, that is good to know. Thank you. And another listener is wondering or says, an old PFRA engineer tells me that a standing wetland will lose a net of 12 inches of water in an average year. Do you know anything about that? Is that right?
Um, Come again? I need to do the calculation. Now, 12 inches, it's about,
Yeah. A standing wetland will lose a net of 12 inches of water in an average year.
yeah, I do a really quick comparisons. It's about similar. Yes,
Okay.
like a 1 inches, it's about 2.5 centimeters or about 250 millimeters, and then 12 about that, or 25 millimeters. So about 12 inches is about 300 millimeters of a year. That's about, yeah, that's what we particularly see in the prairies where you have so that's very significant because in the prairies or the western part, there's actually a transition between uh, the drier regime to the east of a wetter regime. So it's a west to east transition from drier to wetter, where most of the like a long-standing wetland, for example, as you can see this in this figure, that are actually occur in the eastern part of the area, but then the western drier period have mostly called a semi-arid climate,
Mm.
where usually the evapotranspiration will exceed the precipitation. So many of the wetlands will go dry in the part where, yeah, that's about right, similar,
Okay.
the
And does
magnitude.
it matter if a wetland is standing? Do you think the standing part impacts it?
Um, Good question. I think um, it's important. It's important in various way, but if it depends on what kind of impacts or what kind of service you're looking at. If it's for like a so for ducks might use the wetlands in different way, but for the cooling impact, I think
Mm.
it is important uh, because it's, if sufficiently you want these standing waters to support evapotranspiration, right? And then in the figure I'm showing the seasonal cycle, for example, these from spring to summer transition, you will still have this. You won't want to. However, I understand that it's difficult because it naturally has this transition of drying from wet to dry. So all the basic messages, if it's natural, then the drying can go on, but don't. But the advocates here is try to keep them not as much disturbed, these wetlands, artificially.
Absolutely. That kind of leads into the next question. A listener named Michael comments that he's noted in his travels and attending crop production shows that drainage has become big business in the prairies. Do you have any ideas how government agencies could take action on preserving wetlands? I know it's a little bit outside your scope, but we'd love your opinion on it.
Well, um, how governments can take actions
To
to
better
preserve the
protect
wetland, to
wetlands.
protect the wetlands from drainage, right?
Hmm.
Um, I Yeah, I think there's has been a really long debate between, and each provinces and the United States has very different policies. And I think one aspect I can think of is that uh, maybe that's I had coming from a very naive point of view, or maybe, or it could have already been proposed but going on, or perhaps not so feasible, but just coming out on top of my head is to provide subsidy if you preserve these wetlands accordingly rather than
Hmm.
draining them. But that's a very simple idea, but have to be validated or feasible actions. But it has to be that. Yeah, sorry, that's on
Yeah.
top. I can think of, but
No, it makes sense. Like people there, and we have a webinar coming up on Thursday called "Does Drainage Pay?" And Shari Clark with Viera Biological Consulting will be talking exactly about that. So maybe I'll throw a pitch in for that right now. um,
great,
that's
thank you
yeah.
for that.
That's all the time that we have today. So I just want to thank you so much for the great presentation. And like you've really been studying this for a long time and have really gone through a lot of data. So it's really great that you're able to share your perspective and all of your experience with us. So thank you very much. We really appreciate it.
Yeah, thank you, Caitlin, for having me. And I really enjoyed this experience when preparing, and it's a reflection of my studies when I did in University of Saskatchewan. And I really hope these efforts and communications and community supports can keep going. Thank you very much.
Absolutely. You're welcome. To all of our listeners, thanks so much for catching our first webinar of Prairie's Got the Goods Week. I just want to let you know that a recording of this will be available online shortly in the near future. Hopefully today. So if you missed something, feel free to check it out. If you want to share it with your friends, we also appreciate that too. When you leave today's webinar, there'll be a quick 1 minute survey. If you don't mind filling that out, we really appreciate it. So we can do an eighth Prairie's Got the Goods Week. So with that, thank you so much, everyone, and have a great rest of your day.
Bye.
Bye.